Hello, this is the second video of Game Theory Series 2 for OCR Discrete Further Mathematics, and we will see how to formulate an m by n zero-sum game as a linear programming problem. In this video we will use a 3 by 3 zero-sum game as the example, but this technique applies to all m times n zero-sum games. So to find the optimum mix strategy, let's assume that player A adopts strategy P with probability small p, strategy Q with probability small q, and strategy R with probability small r. So P, Q and R will all be greater than or equal to 0, and also less than 1. Because each player must play one or other of the three strategies, for player A, we know that P plus Q plus R must sum to 1. So we need to find P, Q and R such that the value for A is maximised, because we want to optimise the value of this game for player A. Noting again that the payoff matrix shows the game from the point of view of A. So linear programming uses the simplex algorithm to solve problems algebraically, and this is covered in a separate series which you should have watched. To use the simplex technique, the feasible region for the solution must lie completely in the positive quadrant. Hence the cells in the payoff matrix must all be made positive before we start using the technique. However, we can transform the payoff matrix here, which has negative cells, by just adding the same constant number to each cell to achieve this. So for this particular matrix, the minimum number is -4, so we'll choose 5 to add. However, we must remember to subtract this from the value of the game at the end. So adding 5 to each cell, that would be -4 plus 5 would be 1, and then we'd have a 9, a 6, an 8, a 2, a 7, a 6, a 3 and a 4. So given that if the probability of player A playing P is small p, and for Q small q, and for option R small r, then we can work out the expected payoff for this new transformed payoff matrix for A if player B chooses X. So looking down those columns, for X, that would then be 1 lot of P plus 8Q plus 6R. Similarly, if player B chooses Y, it would be 9P plus 2Q plus 3R by looking down that second column, and for Z, 6P plus 7Q plus 4R. And the value of the game is a minimum that A will win. Let's call it V. So to formulate a problem as a linear programming problem, we need 3 elements. The objective function. Well, this is usually a maximise or a minimise, and here we want to maximise P equal to this value of the game for A. The decision variables are these probabilities. P is defined as the probability of A playing option P, Q defined as the probability of A playing option Q, and R. The constraints will be the expressions that we formed when we considered what the value of the game for A would be if B chose either X, Y or Z as their strategy. So we can say that P plus 8Q plus 6R is going to be greater than or equal to the value of the game, that 9P plus 2Q plus 3R greater or equal to V, that 6P plus 7Q plus 4R is greater or equal to V. We also remember that we had that P plus Q plus R, and I'm going to say here less than or equal to 1. I know we said they would sum to 1. But if we maximise V, that will set P plus Q plus R equal to 1. And also we noted that P, Q and R had to be non-negative. So here we have this particular 3x3 zero-sum game formulated as a linear programming problem with the objective function, decision variables and constraints. In the next video, we will see how to solve the m times n game as a linear programming problem and how to interpret that solution.